Hello everyone, and welcome to the next video in the series. This is the first technical skills video on rational numbers, and the topic for this video is on the basic tools that you need to know about in order to be able to work with rational numbers efficiently. Now, to begin, let me remind you of what rational numbers are. Basically, rational numbers are numbers that have the form of p over q, such that both p and q belong to I, so both the top and the bottom are integers, and the bottom number is not zero. Now, I won't get into the details of why we have these conditions, other than to note that I have discussed them in an earlier video, and I refer you to that video on number systems in order to find out why is it that the top and the bottom have to be integers and the bottom number cannot be zero. But I do remind you that integers are numbers such as -3, -2, -1, 0, 1, 2, 3, and so on. The list goes on both sides. And so the top and the bottom can be any of these numbers, and the bottom number cannot be zero. As examples of rational numbers, we have 3 over 4. You notice that both 3 and 4 are in I. They are integers. So that satisfies the condition p and q are integers. And the bottom number is not zero. -3 over 4 is also a rational number. The top -3 is an integer, and the bottom 4 is also an integer, and the bottom is not zero. Same for 3 over -4 and -3 over -4. 0 over 4 is also rational. The top is an integer, the bottom is an integer, and the bottom number is not zero. And so is 0 over -4. This is also an integer. But numbers such as 4 over 0 is not an integer. Now, in this case, both the top and the bottom are integers, but we do have the condition that the bottom cannot be zero. And again, I discussed the reasons for this in an earlier video. We found out that an expression such as 4 over 0 is undefined. It means that it's not equal to any numbers. And 0 over 0 is also problematic because it can be equal to any number. We call these kinds of expressions indeterminate. And for these reasons, division by 0 is not allowed, and we don't call these expressions rational numbers. Okay, as far as the basic tools go, there are 3 of them that you need to know about. And again, a knowledge of these tools will help you immensely in working with rational numbers, in the sense that they make you much more efficient, and the tools that you use start to make a lot more sense. There are 3 of these, as I mentioned. The first one is to know the multiplication table very well. The second is to have a knowledge of prime numbers. Now, you don't need to know a lot about how prime numbers behave, so long as you know what they are and how to use them. And the third, having a knowledge of what we call divisibility tests. These are quick tests that tell you whether one number goes into another evenly without having to do long division. Let's talk about each one of these in turn. For the multiplication table, and of course the question is, do I have to? And the answer is unfortunately yes. That's a very firm yes. And the reason for this is because when you work with rational numbers, the need to multiply and divide is constant. In fact, you'll find by the end of this video that I've divided maybe hundreds of times. And let me give you an example of how it is that division is so common, if you like. Now, one of the things that we do with fractions is, and fractions, by the way, are positive rationals. What we do with fractions is you'll often find that you need to reduce a fraction. That means we need to make the top and the bottom numbers smaller, but keep the overall size of the fraction the same. And one way to do this is to divide the top and the bottom by the same number. And I'll explain shortly why that works, and I will explain again later on in another video coming up on reduction of rationals. But for now, we just go by the rule that we can divide the top and the bottom by the same number. And we take a look at 6 and 8, and we notice that 2 goes into both. And so we divide the top by 2 to get 3, and divide the bottom by 2 to get 4. And you notice that right now we did 2 divisions. And to be able to do division, you need to know your times table. Or let me put it this way. In order to be able to do division efficiently, you need to know your times table. And we can now say that 6/8 is equal to 3/4. Now, both of them have the same overall size. But of course, 3/4 is much easier to comprehend size-wise. That's one reason why we would like to reduce fractions. There are other reasons, like when you multiply and divide, even when you add and subtract, reduction does come in. Okay, let me explain why is it that reduction works. Now, here in the diagram on the right side, we have both 6/8 and also 3/4. With 6/8, the 8, the denominator, tells us how many pieces a 1 should be cut into. 8 pieces. Here we have 1, 2, 3, 4, 5, 6, 7, 8 pieces. And then we take 6 of those. So these are the shaded parts. 1, 2, 3, 4, 5, 6. And so the shaded part is the amount that 6/8 refers to. This is what I get. With 3/4, we take half as many pieces. Instead of 6 of them, we take only 3 pieces. But notice that because 8 became 4, the size of a piece doubled up. Now, of course, 8 gets divided by 4, and the size doubles up because when we have a 4, the pie gets cut into 4 parts. With 8, it gets cut into 8 parts. So the larger the denominator, the smaller the piece of the size. And so what happens when you reduce and divide the top and the bottom by 2? Dividing the top by 2 means you're taking half as many pieces. Divide the bottom by 2 means each piece is twice bigger. And that's how you end up with the same overall amount. You take half as many pieces, each piece is twice bigger. And if you were going to reduce a fraction such as 9/12, 3 goes into the top and the bottom. When you divide the top by 3, you're taking 1/3 as many pieces. And when you divide the bottom by 3, each piece becomes 3 times larger, and the two of them end up cancelling each other's effects. Okay, so for 6/8, it's not that difficult to reduce the fraction. And by the way, I will be, as I mentioned, I will be talking about reduction later on and give you an algorithm for it. But for now, I rely on you having some background. I assume that you have worked with fractions in the past. Maybe you weren't that good with them, but you know what reduction means, even though you might have forgotten how you would carry out a reduction. Okay, so now fractions can become more complicated, such as 49/56, and this is where the times table comes in. If you are good with the times table, you can just look at 49 and 56 and tell that 7 goes in. And not just that, but that 7 goes into 49 7 times, and that it goes into 56 8 times. So 49/56 is the same as 7/8. Now you notice that even if you have access to a multiplication table, it still takes time to reduce 49/56. And the reason for that is because you have to locate 49 on the times table and find out how it decomposes into 7 times 7. You need to find 56 on the times table and see that it decomposes as well into 7 times 8, so that there is a 7 common to both 49 and 56. And then you can go ahead and say that if I take 7 out of 49, I'll be left with 7, and 7 out of 56 leaves me with 8. That's time consuming, and if you imagine if you have to do this all the time, then it becomes a matter of time before you feel frustrated with the amount of work that you have to do. And when you practice the times table, make sure that you practice both going forward and backward. So as an example of that, not only should you know that 7/8 56, but when you see 56, it should automatically trigger a breakdown to 7 times 8. Now, how do you go about memorizing the table? And the first thing to know is what not to do. For one thing, I recommend that you tune out any comments by people who tell you that you don't need to know the times table. And in fact, whether they are ordinary people or mathematicians doesn't matter. I never forget once I was talking to an editor who was actually a mathematician. And he was, when I mentioned the need to know the times table, he was beside himself. He went on a long talk telling me how it is that the times table is not needed, and that he was a living proof of a mathematician who actually didn't know his times table. And my response to that is that precisely what a mathematician does, which is try to find complex relationships between quantities, and for that you don't need to know the times table. You don't need to know how to multiply or divide, so long as you know what multiplication does and what division does. You don't even need to know how to add and subtract, so long as you know what addition does and what subtraction does. Keep in mind, a lot of mathematicians don't even know how to find the square root of 2 by hand, and that doesn't mean that they cannot find complex relationships. But exactly what a mathematician does, which is, as I mentioned, find complex relationships between quantities, is different from the needs of someone who is dealing with an everyday life problem, such as a money problem, where you have to be good with numbers. And it's in that sense that knowing the times table becomes a very, very powerful tool. And in fact, I would say that if you don't have it, it's a handicap. And it's something that I highly recommend that you fix. Now, the other thing to keep in mind is that with, at least in North America, it seems that there is a tendency to teach people how to go all the way to 12 when you memorize your times table. My guess, you only need to go up to 9. But my guess for going up to 12, at least again in North America, is because of the fact that feet and inches are used pretty widely, and because 1 foot is 12 inches, if you're trying to find, let's say, the area of a square that's 1 foot long on each side, that would be 12 inches on each side, and you would have to multiply 12 by 12 to find 144 square inches. And I think that's one of the reasons that in North America they go up to 12, but you need to go up to 9. Up to 12 is pretty brutal, by the way. That's way too many numbers to memorize. Okay. Now, as far as memorizing the table goes, it appears like a daunting task because of all these numbers that you need to know. But the good news is that you don't need to memorize all of this. Let's take a look at the next diagram, where I have highlighted the values that are on the diagonal. These values come from multiplying a number by itself, such as 3 times 3 is 9. Let's say 6 times 6 is 36. And one thing about this diagonal is that there is symmetry about it. So if you think about it, 2 times 1 is the same as 1 times 2, and you don't need to memorize both of them. Let's actually sort of highlight one of them. This one, 2, we don't need to know that one. So long as we know 1 times 2 is 2, it's the same as 2 times 1. Same thing for 3 times 1, which is 3, and 1 times 3, which is also 3. So we don't need to memorize both of those. And same thing for 6 and 6. You see, this one comes from 3 times 2, and this one comes from 2 times 3. So long as you know one, you don't need to know the other. And of course, there is that symmetry about all of these numbers below the diagonal and the ones on top. If you take a look at, let's say, 14 here, from 7 times 2, that's the same as 14 here, which is 2 times 7. So we need to memorize only about half the table. Right. Now, as far as the top row goes, I'm guessing that everybody knows that 1 times the number is the number itself. So 1 times 4 is 4. 1 times 5 is 5. So we don't need to memorize the top row. On the diagonal, most people know that 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and 5 times 5 is 25. Those are normally known, and if your times table is, if you have a decent understanding or control over the times table, then these values you don't need to memorize, you already know them. As far as 2 goes, most people know about 2 times 3 and 2 times 4 and 2 times 5 and 2 times 6. 7, 8, and 9, again, the majority of people know it, but some people might have a bit of a difficulty with them. So now we only have to memorize these ones. As far as 3 goes, usually 3 times 4 and 3 times 5 are known. And as far as 4 goes, normally 4 times 5 is known. So there is not as much that you need to know. So long as you have the basics, then this is all that you need to do. And to memorize the ones that you're not good at, you can make your own problems. Let's say that you want to practice 7 times 8, which is 56. You can make problems for yourselves like, let's say, 717 times 8. And that way you get practice multiplying 7 by 8. Now you notice that I also include some easy numbers like 1. To give your brain a bit of a break, so that you don't constantly say 7 times 8, 7 times 8, 7 times 8, but you go from let's say 8 times 7 to 8 times 1, and then 8 times 7 again, and that way there is a bit of a gap, and then you recall again that 8 times 7 is 56. You can give yourselves other problems like 177 times 8, or 727 times 8, 770 times 8. And you can use your calculator to double check the answer to see if you did it right. But you should actually, I recommend that you practice on pen and paper, using pen and paper. And I also recommend that you stay away from these kinds of tricks that sometimes some people promote, such as how to quickly find the result of a multiplication by using the kinds of tricks that rely on any approach that doesn't include memorization. I'll give you an example of one such trick. Let's say that you want to multiply a number by 9. So you want to know what 9 times, let's say, 7 is. What you can do is you can bring 7 down by 1. So put down 6. And then put another digit that when you add it to 6, you get 9. So that would be 3. And so 9 times 7 is 63. Let's take a look at another one. Let's say that you want to multiply 9 by 5. You bring 5 down by 1, you put down 4, and then put a digit so that when you add it to 4, you get 9. That would be 5. Now these approaches may seem impressive and they may seem like, oh, finally I don't have to memorize the times table, but I can tell you that they are of very little use. For one thing, they are inefficient. If you think about it, I'm multiplying 9 times 7, and instead of saying 9 7 63, I have to say 9 7s, okay, bring 7 down by 1, you get a 6, and then what do I put down to get a 9 3? 63. This is time consuming, this is frustrating, I would say, if you have to do this over and over again. And the biggest problem though is that it doesn't really teach you how to go backwards. When you memorize the times table, you take a look at 63. As soon as you hear 63, again, it's automatic for you to just think 9 times 7, that's it. But if you haven't memorized it, then it becomes difficult to decode 63 to 9 times 7. And that's what you need to know most when you work with fractions, how to go backwards, because we do a lot of divisions. Alright, so let me get rid of everything that I typed here. Okay, and so I do recommend that you also practice both multiplication and division. So do practice that 4 times 7 is 28, but also pick a number from the table like 28, and then see if it brings to your mind 4 times 7. Pick 48. When you hear 48, do you see 6 times 8? If you can do that, then your times table is pretty good. And just before I finish the talk on the times table, I would like to also mention that as far as if you have a child, I recommend that you start teaching them the times table in the middle of grade 3. And by the time they get to the middle of grade 5, they should know it really well. Now, some kids start earlier, some of them later. That's okay. That's not a big deal. But by the time they get to the end of grade 5, actually I would say middle of grade 5, they should know it really well. And also when you start with them, be patient. In the middle of grade 3, you can start with only 2s and 3s. And then in grade 4 you can try 4s and 5s and also 6, and then in grade 5 you can finish it. You notice that as you go down the list, there will be fewer and fewer numbers to know about. On that note also, it pays off if you know the numbers on the diagonal pretty well. So these are one number times itself, like 49 is 7 times 7. Alright, so that's all I have to say about the times table. The next topic is on prime numbers, and I would like to explain why by talking about a particular problem. And this problem says that we want to reduce 78 over 91. Now I tell you ahead of time that the number that goes into the top and the bottom is 13, and we can reduce 78 over 91 using 13. Dividing 78 by 13 gives us 6. Dividing 91 by 13 gives us 7. So 78 over 91 is the same as 6 sevenths. And that's one of the reasons we would like to reduce. You notice that it's a lot easier to comprehend the size of 6 sevenths compared to 78 out of 91, although the two of them refer to the same overall amount. Now, of course, the question is, how do we find that 13? And there are different ways to go about finding 13. Probably the worst way of doing it is to use what we call brute force, which means we'll start with 1, and then we'll try 1, 2, 3, 4, 5, 6, and so on until we eventually get to 13 and notice that 13 works. But this is a lot of divisions. If you think about it, in the best case scenario, which is the case when the top is not divisible by any of these numbers, like let's say, now I know that 78 is divisible by 2, but let's say I had a different number on top. Let's say I had 51, and I know that, and then 2 doesn't work for the top, and I don't have to try 2 for the bottom. So for 2, I have to do one long division to find out whether it works or not. Then 3 comes in. We divide the top by 3, again that's a long division, and we find that 3 doesn't work. Now for 78 again it works, but supposing it was a value that for which 3 didn't work, then I would have to do one division. I wouldn't have to try the bottom, because if the top doesn't work, then I cannot reduce using 3. Then for 4, let's suppose that it doesn't work for the top, so again I do only one division for 4 to find out that it doesn't work. Then for 5, same thing. Let's say it doesn't work for the top. Again, I do only one division until I get to 13, and then I have to do 2 divisions to reduce the fraction. Now, how many divisions is that? If you count 1, 2, 3, 4, and by the time you get to 13, count 2, you end up with a total of 13 divisions using brute force with the best case scenario. In the worst case scenario, each number will have to be used twice. Let's say, for example, for 78 over 91, I divide 78 by 2, and then I notice that 2 does work. And then I have to do another division, divide 91 by 2, to find out that it doesn't work. So now I did 2 divisions to find out that 2 doesn't work. And same thing with 3. In this case, in fact, 3 does work for the top, but it doesn't work for the bottom. So I have to divide the top by 3 to find out that it works, and then I have to divide the bottom by 3 to find out that it doesn't work. So again, 2 divisions for 3. In the worst case scenario, for each number you will do 2 divisions, and by the time you get to 13, you will have 24 divisions in total. Now this is the problem that we have, because this is inefficient. Doing 24 divisions, or 13 divisions even, to reduce 78 over 91 is a lot of work. Keep in mind that each one of these is a long division, and so that's what we would like to avoid as much as we can, doing the long division. So how do we go about doing this? But at some point somebody got frustrated with the amount of long divisions that they had to do, and they started to notice that for one thing, you don't have to try 1, because if you divide the top and the bottom by 1, you get the same numbers back. So we cross out the 1. And then if you have tried 2 and 2 doesn't work, then guaranteed 4 will not work, and 6 will not work, and 8 will not work. Basically multiples of 2 will not work. So let's take those out. We take 4 out, and then 6, 8, 10, And if you do this for the rest of the multiples of 2, all of these numbers that appear in faded color are out now. We only have to try the black numbers now. Now, we did 2, and then as far as 3 goes, supposing 3 didn't work when you try to reduce, so you use 3 as much as you can and eventually it doesn't work anymore, then we don't have to try 6 or 9. These are multiples of 3, so let's take them out, 6 and 9. And then the next one is 12, which is already out. Then the next one is 15, let's take that one out. And if we continue in this manner, we end up with these numbers left. The next number is 5, we don't need to try 4. And if you try 5 and 5 doesn't work, or if 5 works and eventually at some point it doesn't work anymore, then guaranteed 10 will not work, 15 will not work, 20 will not work, 25, let's take that one out. and also 35. So we'll be left with these numbers. And then you try 7, and if 7 doesn't work, then 14 will not work, and 21 will not work. And eventually you'll be left with the numbers that you see, and you may recognize them as prime numbers. Now these are not odd numbers. For one thing, 2 is a prime, but it's not odd. And also 9 is odd, but not a prime. So there is a difference between prime numbers and odd numbers. And these are the only numbers that you need to try when you, let's say, reduce a fraction. Now if we write only these ones down, we end up with this diagram: 2, 3, 5, 7, 11, 13, 17, 19, and so on. I highly recommend that you memorize the list up to 20. The reason for that is because the majority of practical problems get done by the time you get to 20. And so this can help a lot. Now with the knowledge of primes, the number of divisions that we have to do to reduce 78 over 91 goes down by a lot. If you take a look, now to get to 13, in the best case scenario, 1 division for each number. There will be 1, 2, 3, 4, 5. And then 13 works for both the top and the bottom, so 2 for that one. That's 1, 2, 3, 4, 5, 7. So we have 7 divisions. In the worst case scenario, 2 divisions for each. So 2, 4, 6, 8, 10, 12 divisions. This is still too many divisions, but the good news is that it's almost half as much in the best case scenario, and exactly half as many in the worst case scenario. So that's a lot of advantage because it saves a lot of time. Imagine if you're a student and you're trying to work out your homework, and it takes your friend who doesn't know about primes 4 hours to do their homework. It will take you 2 hours because you do half as many divisions. And keep in mind that long divisions are the worst part of dealing with fractions, when you have to do long division. All right. Now, as I said, I recommend that you memorize the list up to 20 at least. If you have the patience to go up to 100, that would be fantastic. All right, we can do better. There is a kind of test known as a divisibility test. These tests are sort of like quick ways to determine whether one number is divisible by another without having to do long division. Remember that we want to cut down on the number of long divisions that we have to do when we work with fractions. So, for example, if I want to figure out if a number is divisible by 2, I don't have to do long division. I can take a look at the rightmost digit, and if it's 0, 2, 4, 6, or 8, then the number is divisible by 2. Otherwise, it is not divisible by 2. So if I want to reduce 6 eighths, and let me put the primes back up. Okay, so if I want to reduce 6 eighths, starting with 2, I'll take a look at 6 and notice that 2 does go into 6 because it's even, and same thing with 8. Now that I know that 2 works, now I divide. I divide 6 by 2 to get 3, and I divide 8 by 2 to get 4. So we get 3/4. For 3, there is a test. Most people don't know about this one. It's actually a very interesting kind of a test. And it says that a number is divisible by 3 if the sum of its digits is divisible by 3. Otherwise, it is not divisible by 3. As an example of this, let's say that we want to reduce 42 over 57. Now, let's start with 2, the first prime number. I can see that 2 goes into the top. 42 is divisible by 2. You notice I'm not doing any long divisions. But 2 doesn't work for the bottom because it's odd. 57 is odd. And therefore 2 will not go into 57 evenly. And so I'm going to skip 2. You see, so far I've done no long divisions. Rather, what I did to see if 2 works, I used the divisibility test for 2. For 3, we add the digits on the top. 4 plus 2 is 6. And that means that 3 goes into 42 because 3 goes into 6 evenly. 57, if I add the digits, 5 plus 7 is 12. And 3 goes into 12 evenly, and therefore 57 is divisible by 3 as well. Now, this is a very interesting kind of a test. And a proof of it I've given in my textbook, Style in Technical Math. In one of the appendices, I've given the proof for it, and maybe in a future video, I will talk about that as well. put the proof online. But for now, you can trust me that this test works. It works for 3, by the way, and 9. Don't try it for other numbers like 5 or 7 or something like that. Okay, so add the digits on the top. 4 plus 2, 6. 6 is divisible by 3. 42 is divisible by 3. Add the digits down here. 5 plus 7, 12. 12 is divisible by 3. So 57 is divisible by 3. Now that I know that 3 works, now I do a long division. 42 divided by 3 and 57 divided by 3. And that leads us to the value 14/19. You notice that if I didn't use divisibility tests, even if I know the primes, in order to reduce 42 over 57, I would have done 4 divisions. Divide the top, or at least 3 divisions. No, 4 in this case. You divide the top by 2, and because it does work, you have to divide the bottom by 2 as well to find out that it doesn't work. That's 2 divisions already. And then when you get to 3, you divide the top and the bottom by 3 and find out that 3 works. So 4 divisions. Whereas if I include divisibility tests, the one for 2, then the number of divisions was reduced to only 2. I take a look. I don't do a long division. I take a look at the top. It's even. 2 goes in. 57 odd. 2 does not go in. No long divisions. Skip 2. And then 3 for the top. Add the digits. 4 plus 2, 6. 6 is divisible by 3. So 42 is divisible by 3. 57. 5 plus 7 is 12. 12 is divisible by 3. So 57 is divisible by 3. And now that I know 3 works, I do 2 divisions and find 14/19. So without divisibility tests, 4 divisions. With divisibility tests, 2 divisions. Again, half as many. For 5, there is a test. Now, this is a test that most people are familiar with. And this one says that a number is divisible by 5 if its rightmost digit is either 0 or 5. That should make sense, because if you think about multiples of 5, they all end in 5 or 0. 5, 10, 15, 20, 25, 30, and so on. And so a number that ends in 0 or 5 is divisible by 5. Otherwise, it is not. As an example, 30 over 35. Let's start with 2. 2 goes into the top, not the bottom. I'm using the divisibility test for 2 here. No long divisions. And then I move to 3. 3 works for the top. 3 plus 0 is, well, you should know that 30 is divisible by 3, but even if you went with the test, 3 plus 0 is 3, and 3 is divisible by 3, so it's 30 then. But 35, it doesn't work, because if I add the digits, I get 8, and 8 is not divisible by 3. So we move on to 5. Now for 5, the top ends in 0, the bottom ends in 5, so the top and the bottom are divisible by 5. And now I divide, and I find that we get 6 over 7. Now 10 is not a prime, but we find that it's useful sometimes for us to use 10. And so the divisibility test for 10 is that the rightmost digit must be 0. Again, that's sort of obvious given that multiples of 10 end in 0, like 10, 20, 30, 40, and so on. So if I want to reduce 30 over 200, I can divide the top and the bottom by 10 and end up with 3 over 20. That has led some people to say that you can cancel out an equal number of zeros on the top and the bottom. So you can cancel 1 0 with 1 0. That's like division by 10. And so if I know about primes and divisibility tests, let's see how many divisions I have to do now before I get to 13. So for 2 I won't do any divisions. For 3 I don't do any divisions. For 5 I don't do any divisions. I do 7 for the top and it doesn't work, that's 1. I try 11 for the top and it doesn't work, that's 2 divisions. And then I try 13 and I get 2 divisions for that one, so for a total of 4. In the worst case scenario, 2 for each, not for 2, 3 or 5, but 7, 11 and 13 for a total of 6. And you notice that compared to brute force, these are a quarter as many divisions, and the numbers are sort of becoming sort of reasonable for a problem that's not so easy, such as the problem that we had where 13 only went in. Okay. So now so these are the ones that I recommend that you know. Then know your times table pretty well, know your primes, and know the divisibility tests for 2, 3, 5 and 10. So basically these are the numbers that you should know very well. You should memorize the list up to 20 for primes, and for divisibility tests know the numbers 2, 3, 5 and 7. Quick ways to tell whether a number is divisible by 2, 3, 5 or 10 without having to do an actual long division. Okay everyone, thank you very much for watching this video, and in the next video I will start to talk about the structure of rational numbers, and this is where I will talk about both how we go about reducing fractions. So I will give you an algorithm at that time. And I will also talk about the different kinds of fractions, which are proper, improper fractions, and as well as how mixed numbers enter the game. Okay, have a great day everyone, and I'll see you in the next video.